Okay, so we go over Newton's method of determining the roots of a function. So to just help us understand, let's say we have a graph. This is our graph, something like that, curving upwards. So this is the way it's going to work. So let's say you have a point x1. So we give you a certain x coordinate that is closer to the root. So of course we are talking about the root to be a part of a function which where it gets to cut what? The x-axis. So we'll call this f of x. Okay. So according to Newton's method, the idea is if you try to use the given coordinate x1 and you try to substitute in the given function, you notice that it's going to give you a certain value of what? Of y. So in this case, the value that you're going to get is going to be somewhere there. Okay. So at that point, what you're going to do is you need to draw a line. So you need to draw a line that is going to be, of course, a tangent. To be more specific, we need to draw a tangent to that point. So something like this. Let me use a different color so that it appears, comes out. So you draw a tangent to that point where you found the function at x1. So we'll call the next point to be x2. So we'll call that to be x2. So you now have x2 there. So again, we'll do the same. At x2, we can also now find its value of a function. So that's what we're going to get, a certain point somewhere there. Okay. Again, we'll do the same. We need to draw a tangent to a curve at that given point. So something like that. Okay. So you notice one thing that is common about all these points that we've come up with. As we continue drawing the tangents to the curve at the given points that we are finding, as we get to draw the tangents, we're getting closer and closer to a point where the curve of a function cuts what? The x-axis. So as we can see, if we try to check the values that we have, x1, x3, so each time we draw a tangent to a certain point on a function, we're getting closer and closer to where the function actually cuts the x-axis. So this is what we call Newton's method of determining the root of a function. So now, it's not always possible that we are going to be drawing on a curve. So now that we know the way the function behaves, or the way the method helps us to find the roots, we can now put it in terms of an equation to just see the way it's going to be working. So let's look at the first coordinate that we had. So given a certain value x1, which is closer to the root of a function, after substituting into the function there, we can agree to say what we had is, so say x1, comma what? The function itself, which is f of x. So at that coordinate, we have x comma f of a function. Okay, what else do we have? So now, one thing that we know is that at any given point of a function, the gradient is determined as what? The derivative of a function. So we can call therefore our gradient m to be equal to the derivative what? Of a function at that given point, which is x1, of course. Okay. So now we know the gradient and we know a certain coordinate that is part of this tangent. So our goal is to get to find the equation of this tangent. And how do you find the equation? So there are two main ways. Of course, with this form y is equal to mx plus c. That is the form of our equation of a line. Now what we're going to do is we'll use the other method that we get to use, which is y minus y1 x. Sorry, so I have m and then x minus what? x1. Now this is the form that is going to help us find the equation of this tangent. Now what we get to do is the value of y maintains, and then we'll plug in the value of the gradient and also y1 and x1. So y will maintain y. So y And then the y coordinate at this point is the function of what? Of x1. As we can see, after substituting x1 in the function, f of x1, that is what is our value of y is. So write that f of x1 equal to, now the gradient is what? The derivative of a function at that point, which will also say f of x1, so prime because it's the gradient. And then in the brackets where we have x, I'll write x, and then I'll subtract x1 itself, because we are saying this point was what? It was x1. That was the value of x. So we can try to simplify this. We can try to simplify it. So we have y minus f of x1 equal to f prime x1. So let me just expand the other side. I'm just expanding the other side so that we have something like this. So we have y minus f of x1, and then if I try to open the brackets, so I have f prime x1 multiply against x, and then the other part I have again f prime of x1 multiplying against x1. So I've just substituted or distributed the derivative of a function to everything that was in the brackets. And now at this point, what can we do? We can now look at the second point, which is also part of the same line. What can we say about it? So x2, on this very tangent that we had drawn, x2 is a coordinate on the x-axis, which implies that the y is equal to 0. So it's x2 comma what? Comma 0. So we can use that to substitute in the function where we have x and y. So if you want, you can substitute from this point, but I can just substitute from the second point where there's y and x. So where there's y, I'll put what? So it was a 0. So it's just more like not even indicating that. So it says it was a 0. And then we're going to remain with negative f of what? x1 equal to f prime of x1 multiplying against what? So the value of x at that point was x2 minus f prime x1 x1, right? Okay. So now, what is the method trying to tell us? What we're trying to do is come up with an equation that will help us predict the next value closer to the root. Okay? So if you have x1, are you able to predict x2? And if you have x2, are you able to predict x3 until you get closer and closer to the root itself? So in this case, since we've used x1 and x2, let's try to come up with a formula of finding x2. So we can take the part having x2 the other side. And what we're going to have is f prime. So let me just now remove this other part since we now know what we're talking about. Okay, so I'll just continue from this other side. So at this point we have negative f of x1 being equal to f prime x1 x2 minus f prime x1 multiplied by x1. So as we move to the next stage, what can we do? So we're trying to make x to the subject, so I can take this part the other side so that we have negative f prime x1 multiplied by x2 equal to, now the other side, this one can go the other side so that we have positive f of x1, and then what else do we have? So I have this part which had remained minus f, so I remove this part, so prime x1 x1, right? So we can try to divide now by this other part. So x2 is going to be equal to the other side, which is f of x1 minus f prime x1 multiplied by x1. So this is all going to be divided by, so I'll divide individually, so by negative f of prime x1, and then the other side as well, negative f prime x1. So the one that is negative will become positive. So our x2 is going to be, I'll start with a positive part, which is this part. So we're going to have a positive what? Now notice as well that this is the same, so we can divide and give us a 1. So that will just remain with positive x1, and then minus function of x1 divided by the derivative of what? Of the function at that given point 1. So now this formula that we've come up with is what we call the Newton's method. So how do you look at it? So the basic idea is, if you go back to the graph that we had, okay, of that form, and then you have something like this. So the idea is, at that point, when you have any given value, let's say x1 at this point, so you find the value of y at that point, and then you draw a tangent to that point. So now this method will help you find x2. So if you can find x2, you can also use the same method to find what? x3. So you just be changing. So it's like you find the next value closer to the root by what? By using this formula. So if this is the way it is for x2, for the third one, I'll say my third value closer to the root is x2 minus the function of x2 divided by the derivative of what? Of the function at that very point x2. So this is the way you can remember this formula. So how can you make it easy for yourself? So just think of it in this way. It's like I'll find a certain point x2 when I have a preceding value x1, and then I'll just subtract the function itself, y, over what? Y prime. Of course, at the given value itself. So this is the way it's going to work for you. So this is what we call Newton's method. It's very easy and very helpful when you're trying to find the root. So check out for the next video where we'll look at some examples on how we get to work with this formula and get to find the roots of given equations. So thank you very much for taking time to watch, and have a lovely day.